My name is Yusuf. I am a principal software engineer at Snowflake. I am an engineering lead in the Snowflake AI research group, and I also lead the Copilot project in Snowflake. Today I'm going to talk a bit about the recent research that we have shared from Snowflake. We'll talk about a large language model and how we trained it, and get into some of the details of the insights that we have learned along the way. So just to set the stage, the Snowflake AI research team has been building a large language model since roughly the beginning of this year. And we, at the end of April, we open sourced it with an Apache 2 license. And we've been also sharing learnings and insights that we gained along the way. And this talk is essentially a walkthrough of all that material. And I hope to focus more on the learnings from open source contributions and sort of focus on the areas that we feel like haven't seen much information sharing recently. And the model's name is Arctic. And I'm going to get into the details of how Arctic is different and why it is important. So just to set the stage, we have looked into quite a few benchmarks while trying to train this model. When it comes to large language models, it is pretty common to focus on a few well-known academic benchmarks that gives an understanding of world knowledge or math skills that the model has. There are these very, very common benchmarks called MMLU and GSM-8K, for example, that most of the labs that develop large language models talk about. At Snowflake, when we talk with customers in the enterprise space, we have seen that there are a few other skills that come up quite often. They generally want to build data copilots that are good at SQL generation. They would like to work with agents that can do coding well, and also they would like to develop LLM applications that can do instruction following at a reasonable level. So we basically decided to focus on this concept of enterprise intelligence and define that as a combination of SQL generation, coding, and instruction following skills, and said that we are going to optimize our model Arctic for that. And the hope here is that, again, it maps better with the needs of an enterprise customer space. And also, we felt like this would actually help us differentiate and contribute better to the open source community as well. So the benchmarks that I'm talking about may evolve over time. So for the initial launch, for SQL generation, we used this commonly coded benchmark called Spider. For coding, we used human eval and MBBP. And for instruction following, we used IF eval. But the tasks that are attributed to these benchmarks, we expect to kind of remain the same. So as the models will get better, as Arctic gets better, or any other that focuses on these get better, we expect we'll focus on new data sets, new eval benchmarks, but the tasks will roughly remain the same. And just as an intro, Arctic essentially excels at enterprise intelligence tasks for SQL generation, coding, and instruction following, while remaining a top-tier model for everything else, like world knowledge and math skills and common sense reasoning. And another important sort of aspect of it is it does this while staying highly token efficient. This is true for both training and also inference. It is a mixture of experts model with 480 parameters. It has 17 billion active parameters, so much fewer of the total parameter count is activated during inference. And also, while training this, the team has co-designed the system and architecture at the same time, and this allowed us to spend a relatively small amount of compute, 3,000 GPU hours. This is on H100 nodes, P5s in AWS, and use only 3.5 trillion tokens while gaining this top-tier performance. So it was the experiment here was obtaining a highly token-efficient system for training, and then a highly efficient model for inference, while being able to achieve these top-tier skills. And this goes without saying, we could not have done this without the many mountains of open source work that came before us. For both pre-training data prep, actually obtaining the data itself, actually figuring out how to prep the data. Then for training and inference, we used many open source systems. Actually, members of the AI research team has contributed to some of these projects before. And the idea here is to basically share how we did this, and then continue this tradition of openly sharing the insights that we have gained along the way. So today, I will walk through the development process step by step. I'll start from pre-training data, how we obtain the data, how we prep for it. Then I'll talk about the training and then serving related details. And while doing this, I'll try to mention the open source libraries involved as much as I can, and then share insights and lessons learned along the way. And finally, we'll end with a list of calls to action and give you information about where you can get more detail about this. One thing I'll keep mentioning is we started this series of blog posts after the launch. We are calling this a cookbook. Right now, I think we are at 4 blog posts that share insights about the training process and other details. And we have a list of things that the team has drafted as well, so we are continuing to publish this. Many of the material, actually, I'll talk about today are essentially a summary of that content. So at the end of the talk, I'll talk about how you can get into more details as well. So just to sort of set the stage, again, the advances in capabilities of large language models has been at a breakneck speed, almost at a weekly basis. Maybe for this week, it's on a daily basis. We've seen many new developments. These are essentially resetting state-of-art when it comes to large language model capabilities. And there is a healthily growing open source community around this as well. Especially recently, there's been a lot of work that has been advancing state-of-art and also increasing hope that open source large language model development can actually catch up to some of the more sort of higher level skills that are sought after. But one thing to note is that the amount of research and insights shared has been decreasing. Lots of open source models out there, but for example, when it comes to data-related insights, there is not much research that is shared. And the hope here is to actually provide some more insights about the work that goes to training these models. And again, I'll intentionally focus on the data insights here because we feel like this area has been seeing less and less sort of information sharing. So I borrowed this from Andrej Karpathy's introductory talk on large language models. When it comes to going from zero to deploying a large language model, there are quite a few steps involved. You have to first start from downloading terabytes of text and prepping it for training. And then you need to get a cluster of thousands of GPUs. You need to figure out how to efficiently compress all this knowledge into your LLM. And then this process usually takes multiple weeks. Then you obtain a base model. Then the next stage is about fine-tuning the model. You need to obtain hundreds of thousands or millions of high-quality labeled Q&A responses. Then you run a fine-tuning job on your base model. This usually takes much less compared to the actual pre-training. Then you obtain your fine-tuned assistant model. Then you run a bunch of evaluations, and then you deploy your system. And the deployment, for example, has actually seen a lot of interesting innovations as well. As the models have gotten more and more complex and larger, there are new challenges, there are new skills that the models develop, and they can actually do much more, but there are new challenges that come along the way in efficiently serving these models. So today, I will sort of break this down into a few components. I'll first talk quite a bit about the pre-training data prep that went into Arctic. And then I'll talk about the system and architecture design. I'll talk about the training optimizations the team has done for prepping Arctic. And then we'll have a few slides about the fine-tuning. And then finally, we'll end with serving-related details, how you go from a ready model to getting it in the hands of users, getting it in the hands of the community, and what are the options available for that. Right. So just to get started, for pre-training data, we have published this blog called Arctic's Approach to Data that, again, gets into the details of all this work. All of the material here is actually a summary of that blog. And again, I'll link to the cookbook table of contents at the end of the talk. Usually, when it comes to pre-training large language models, we can sort of look at four different categories. There is web data, which is usually the largest category across all data, that comes from a bunch of large libraries that are well known. Or if you have your own crawl, you can also use that for the web data portion as well. Snowflake acquired this company called Niva a year ago, and that company was a consumer search company, and it had its own crawl as well. So some of the experiments that we have done is across these large libraries of data. Some of it is on Snowflake's own crawl as well. And for coding, usually this data comes from the web again. There are also a few common libraries, but relatively smaller size. So most of the data comes from publicly available GitHub repositories. And when it comes to coding, there are interesting nuances around dependencies. How you order the data matters quite a bit in the model's understanding of the coding skills needed. And finally, for STEM, this is usually books and academic-related content, and it's relatively a small number of data sets are available for books and academic content. So when you look at the breakdown, it's usually the large portion of the data sets used in pre-training is coming from the web. Then it is coding related. Then again, it's a much smaller portion is from STEM. which is the case for us as well. This breakdown is just for an initial phase for Arctic training, just for the first trillion tokens. I'll talk about the final breakdown and the stages at the end of this portion. So getting to a high quality pre-training data set involves a few steps, and I'll sort of break this down to three. First, I'll get into the details of what we did about the web data, where we obtained it, how we filtered it, what tools we used for this. And then I'll talk about gathering high-quality enterprise-focused data sets. These are mainly coding and SQL-related data sets. Again, the objective was to optimize for enterprise intelligence, and the main sort of data sets that will contribute to this will be coding and SQL-related data sets. And then finally, I'll talk about some data processing techniques used for both cases, for both web and coding, and the pipelines that we use to refine these the data quality here. So for web, there is actually two well-known large data sets that are known to be very, very high quality. The first of these is refined web. This is a data set that was created while creating the Falcon large language model. And that team basically published a lot of good details about how they obtained refined web, and it is sort of seen as a fairly high quality data set. So we used that, and also we benefited quite a bit from the insights that they have shared in that paper. Then there's C4, which is a high quality distillation of Common Crawl. Common Crawl is an open source project that provides a sort of distilled crawl of the web. And this is sort of an ongoing project, so you get sort of new dumps of Common Crawl regularly. And C4 was a data set obtained by distilling this and obtaining a high quality subset of the Common Crawl set. And again, these two comes with language filtering, deduplication, and quality filtering on their own. But while talking about refined web, for example, they talk about using this other model called CanLM and its perplexity score to get a better understanding of how a new data set is in terms of quality. So CanLM is trained on Wikipedia text. And what you do is, when you look at any new data set and compare with CanLM's perplexity score, it gives you an understanding of how similar the underlying data set is to Wikipedia content. This gives you a measure of quality. So you can essentially look at CanLM perplexity score and threshold from a certain value. And the team did that for refined web and C4, which reduced the number of documents by roughly 20% or so. So from these two, we obtained a web data set of 750 billion tokens or so. And this actually formed the initial high quality reference data set for us. So we needed much more web data, but again, usually when you're generating high quality subsets from a larger pool, you need a reference set where you can say, okay, this is high quality, so I'm going to start comparing the effects of any new candidate set to the effects of this high quality data set. And then you run a bunch of ablations, experiments where you train with the high quality set, then you train with the candidate set, and then you again compare the final result. As you do this, you get a better understanding of how you can obtain better and better subsets and increase the size of your high quality data set. So for this pool of the remaining web data, we used common crawl dumps from together.ai. These are not only sort of data, but also a lot of annotations, including perplexity score and other useful signals that comes with it. And the process here is, again, we have a high quality data set coming from refined web. You can train a small model with that, and then you can filter across your all these useful signals and obtain a subset from the common crawl dump. And then you get that subset, you get refined web, you compare the two by training a small large language model and looking at the benchmark scores for those two. And you find the right configuration of threshold values for all these annotations through that. One interesting note about common crawl quality, when we started this process, even with a seemingly reasonable filtering configuration, there was still a lot of quality gap between refined web and what we were obtaining from common crawl. And after investigation, the team found that this gap is mostly coming from the fact that we were paying attention to the latest dumps from common crawl. When we actually looked at the whole sort of timeline, the quality jumped, and we are still unsure why this is the case. One hypothesis is that recent years, common crawl has been blocked more and more on the web, and this might be actually resulting in declining quality in the recent years, and maybe that's one of the reasons. But again, by just focusing on the whole timeline of common crawl, we were able to match the quality of refined web, and then we use this to obtain more and more, to basically increase the web data we can use beyond the initial 750 billion tokens. And just to give a bit more details about the tools that we are using here, you can basically write a human rater tool in less than a few hours using Streamlit. Even when you're new to Streamlit, it makes it super easy to sort of generate these tools. And then what we did was we both handled the thresholding and obtaining these subsets in Snowflake. Then the eval results were also stored in tables in Snowflake. Then you can kind of get feedback on data quality. You can compare different subsets in terms of quality. This is a screenshot from that tool for one of the ablation runs that we have done. And through the course of this process, you run many ablations. You get many sort of small subsets of web data. Then you look at the performance of these new models that are trained across benchmarks that you care about. These metrics are what we are calling common sense reasoning metrics. These are sort of pretty sort of commonly used in the industry. And the idea is if a subset is providing a good jump in terms of performance in these metrics compared to refined web, that should mean that it's as high quality as refined web. And again, this is the comparison against refined web, and this is filtered plus latest is the latest common crawl, and filtered plus all is the all common crawl. And the idea is to find the configuration of annotation values, thresholds, that we are going to use to filter across the whole data. So that's for web data. And we'll talk a little bit more about the signals used here. When it comes to enterprise-focused data sets, again, there is a few sort of commonly known to be high-quality coding-related data sets. StarCoder is a large language model, and there is the data set that was used to, the coding-related data set that was used to train that was also open source, so we used that. That is known to be a high-quality data set. There is also a data set called GitHub, which is a relatively small data set, but again, it's known to be high quality. And there's also PyPy. On top of these, we crawl GitHub public repositories, and we focused on repositories with at least 10 stars to get an initial baseline of quality. And then we essentially mapped the content and the content hash obtained from these to a single table. Then there was another table that contained the content hash and the metadata related with this code. And again, the idea is to add a few more signals that would be used to threshold and filter across the initial pool. Then you converge on a configuration that will give you a high quality data set. Then you can use the first table here to map to the right list of content hashes, and then you can obtain the actual contents through using the second table. And here for coding, there is a few sort of recommended signals that you can obtain. These are again coming in as additional columns to this metadata table. You can, for example, compute whether it's the underlying content is a noisy XML file or a noisy YAML file, likewise JSON, HTML. You can look at the maximum line length in the code repository in question. You can try to get an understanding of if the repo is a duplicate or not. There's a bit you can obtain from the GitHub API called GitHub fork bit, but it's very common to make a fork of a repo without using that as well. So the team had to sort of also look at commit history and compute whether a repo has a duplicate or not. And then another sort of last interesting signal is whether the underlying repo has any decontamination in it. These benchmarks are becoming more and more common. There are a lot of large language models, so there are a lot of repos that actually contain MMLU, GSM8K related data, GSM8K related code. So we also had a bit that was looking at whether there is any similarity between the underlying content and any common benchmarks. There are a lot of MMLU sort of copies out there in GitHub repos. So this was useful to avoid decontamination in the training set. And here's just a sort of a screenshot from how you can do this in Snowflake using, for example, a user-defined function in Python, where you obtain. I think this is for the noisy HTML function, and then you can essentially define a Python function that you then use to create a column within your table, and you know, Snowflake makes this fairly easy, and then you can apply different thresholds across that table and obtain your data set. Another sort of important thing to note in looking at enterprise-focused data sets is, as I mentioned, the dependencies involved. There's another large language model called DeepSeek Coder that gets into the details of why this is important and how this is done. So you learn quite a bit from that. And what they do is they don't only just get the coding-related data, but they also topologically sort all the files within a repository in the order which they're imported. So they initially break down repositories by programming languages, then they build a dependency graph across this, and then they traverse this graph to produce a single large document per repository and language that contains all the relevant files. Sorting the dependencies topologically seemingly improves the coding understanding of the model. From the ablations that we have run, at least the experiments indicated that you can also still get benefits from the ungrouped form as well. So the coding-related data set included both the topologically sorted version and the ungrouped form as well for us. Then, when it comes to other data sets, there are a few that I can mention here. Of course, focusing on SQL generation, turns out Snowflake documentation is very handy for that. So we had a bunch of Snowflake documentation in the training set. We had a few data sets around math. Open Web Math is a good one that gets into STEM knowledge. Cosmopedia is a synthetic data set that I think replicates Wikipedia articles using open source language models. And then Open Web Text is a replication of web text data set that was used in the GPT-2 paper. And we use these as well. So when I mention other, that category contains these data sets. And finally, when it comes to data processing techniques, one thing that you worry about is redundancy within your data set. For us, this meant looking at the frequency of n-grams and threshold them according to a minimum value. We also looked at things like word length, number of ellipses, number of bullets as quality signals. So again, you look at these values and then you threshold according to a certain value, and that becomes your configuration, and then you do many ablations or the larger pool to obtain the right configuration. And again, we use the Wikipedia-based CanLM model to look at its perplexity scores to get a better understanding of how the underlying web data matches with Wikipedia quality and content. And many of these ideas are actually referenced from the Refined Web C4 and Gopher papers. So for details and small variations on how they approach this, I would defer to those papers. And then another sort of important aspect of data prep is deduping across your data sets, especially for web data. If you have many larger pools that you start from, it is recommended that you have less duplication across your web data set. And we used a combination of MinHash and LSH pipeline to do deduplication. There are a few challenges here. The initial challenge here is if you try to look at MinHashes and across different sort of content, and you get pairs and start comparing these MinHashes, it gets quadratically complex. To kind of handle this fact, the team essentially broke the MinHashes into subhashes, and if the initial subhash matched it, the underlying contents were grouped together, and this allowed us to basically reduce this problem to a linear lookup. And another aspect here was when you actually just look at the size of these min hashes, in some of these data sets, they can grow exceedingly large. There again, we used these min hash partitions that are smaller in a Snowflake table, and then sort of essentially broke this problem down into a SQL query, then perform the window function to keep only one instance of the subhash. In the end, the model was trained across 3 different phases. Again, 3.5 trillion tokens in total. From ablations that the team has run, our understanding was if we start from a breakdown that is more web-focused, and then added the coding-related data over time in the 2nd and 3rd phase, we would obtain better results. This slightly differs from common practice, where your sort of breakdown of web to code to STEM is constant over the course of all training. So we did this training with a curriculum and 3 phases. And the breakdown here is also shared in the blog post as well. So I think this finishes the sort of details about the data prep. Next is picking the right architecture for the model, and also the system level optimizations you can do to get an optimal training setup. We have published 2 blog posts about this. One focuses more on the mixture of experts architecture used and the sort of trade-offs that went into it. The other focuses on system-level optimizations, kernels that was written for efficiently training the model. And this is a very sort of short summary of the content from that. As an introduction, most of the models, Llama 2 and 3, for example, the ones that has been published so far are dense transformers. So that means in each layer there's an attention module followed by a single feed-forward network. And in a mixture of experts setting, instead of a single feed-forward network here, you have a few of these. And then there is a gating function that routes each token that are coming from the attention module to either one or more feed-forward networks. This is called mixture of experts. Each of these single blocks, block is called an expert. And the idea is, if you have many experts, you can store more knowledge, you can obtain higher complexity in your system, but that comes at a communication cost, and also the training becomes a bit more challenging as well. But essentially, it allows you to increase the number of parameters in the model while being able to still train efficiently and also run inference efficiently. So in general, even though you have many experts and these sort of feed-forward networks are duplicated, when you run inference, you only route your token to a few of them. There is usually, again, a gating function that maps to the right experts here. The architectural choices ranges from deciding on how many layers, across how many layers you're gonna repeat the MOE part. So you can essentially say, I will interleave between dense layers and MOE layers, and say every other layer gets an MOE layer. Or you can say every layer actually is a sort of a repeated version of this architecture. And another thing is the gating function can route to the most important expert. This is called top 1, or it can route to more than one. It can be any sort of integer value. It's called top K selection. And Arctic was trained with top 2. So at every token, it was routed to 2 of these experts. Of course, because this allows you to sort of have a larger model with better skill sets, you would want to increase the number of experts if your system actually allows it. But again, that introduces a lot of communication overhead and complexity in training. So there is usually a trade-off there. Arctic was trained with 128 experts, so it has 128 experts at every layer, and it selects the top 2 for every token again. And actually, most of the work has gone into being able to do this in an efficient way. And some of the sort of insights shared in these blogs actually gets into the details of that. It is more common to have 8 experts per layer, for example, in the open source models that you see out there. Mixture of experts itself is relatively new to the open source community as well. So maybe even 6 months ago, we would only have 2-3 organizations with proprietary models only, a few papers that talked about MOE architecture and how it can be trained. Now, this is becoming more of a common practice. And another sort of different aspect of Arctic is it doesn't use a traditional MOE architecture as well. One insight was when you have many experts, this creates a lot of communication overhead, so you inevitably spend a lot of time just routing data across your system. And one insight was if we have in each layer, if we have a dense component as well, then you can still train that dense model while also routing your information across your many experts. So Arctic was trained with a hybrid model, hybrid architecture that combines a dense transformer with an MOE hybrid transformer. So essentially, in every layer, there are 2 branches. One of them is an MOE branch, and the other is a dense branch. Now I'll talk a little bit about the optimizations that the team has done. It is very hard to do justice to this part in just a few slides, so I'll refer you all to the actual blog post for the details. For training, we used this library called DeepSpeed. Actually, several members of the Snowflake AI research team were founding members of the DeepSpeed project as well. In this library, there is a method called zero, and it allows you to partition your large language models, optimizer states or gradients and model parameters across different processes. So for any training, you have a large batch of data, and the initial sort of optimization you can do is you can parallelize the batches of data that is processed in your system. This is called data parallelism. So you use different sort of batches of data, and then you have to sort of sum over, for example, the gradients of these computations. If you partition your optimizer states across your data parallel processes, this is called stage 1, zero stage 1. And if you also partition your gradient values, this is called zero stage 2. And if you also partition your model parameters, so if you actually break down your layers and sort of shard them across different devices, for example, this is called zero stage 3. And for Arctic, again, there are 2 branches. There is a dense branch, and then there is an MOE branch. For the dense branch, the team has used zero stage 2 across all GPUs. And then, because it's an MOE model, another sort of degree of optimization comes from looking at the different experts and actually sharding them across different devices as well. This is called expert parallelism. So again, in Arctic, the team used expert parallelism to distribute the experts experts among E number of devices. The E here is 128 for Arctic. And also again, 0 stage 2 for further scaling all the experts to all the remaining GPUs. So one way to do this is in a sort of in E devices you have a copy of the dense branch, and then your first expert, then you stride starting from the first expert to the end, then you start from the beginning, and this is the sort of the data parallelism come across these two different processes. So when you're computing gradients, for example, you have, this is called an all reduce operation. You have to kind of communicate the gradient values across these two processes and obtain your final gradient. And also for some of the operations during training, you still need to communicate throughout all the different experts here. That's called all-to-all. And depending on how you order the experts, you get different communication trade-offs again. I'll get into that in a second, actually. So the main bottlenecks that you see while training this large MOE model is, first, there are a few sparse operations that are inefficient by their nature. Again, this goes back to the custom architecture that causes a few not commonly seen operations to be inefficient. So the team has had to write custom kernels for these operations. Then there's a method called activation checkpointing, and there were a few things that the team has added to obtain a better activation checkpointing setup. So the idea here is you cache the activation values for the system during training, and because there is a large number of parameters for Arctic, we realized that if you quantize your activation values and write them to memory, and then you dequantize back and use them, this actually is faster than sort of getting rid of all of them and recomputing them. So that was one level of optimization. And then another thing was the communication overhead, again, was fairly large because of the architecture of the model, and there were a few trade-offs that the team had to sort of look into there. When it comes to these sparse operations, just to call out, there were essentially 4 custom kernels that was written. One was about that initial routing layer, so the output of the softmax layer for the output for the attention layer, essentially connecting it to the router. This looks at the top K experts that that will be used to communicate a token. So given a token, where do you send that token among many experts? And this computes that. Then one issue with a mixture of experts is if you end up routing your token to the same expert over and over, this will create a instability across your system. One of your experts will learn more than all the others. So you have to actually keep track of where your tokens are going in a single sample. And then if you have to basically put a threshold to the number of tokens an expert can get during a single computation, then when one of them, or when a few of them are saturated, you have to kind of use a random selection to map it to the right experts that are not been training. And then there was a kernel associated with that as well. Then these two essentially creates this mapping and then there's a dedicated kernel for actually moving the data across and scattering them across the experts. Then there's another dedicated kernel for after the experts get their results, gathering them, and then routing them to the output. One final thing to mention here, again, the team used an expert parallelism and data parallelism in combination. You can essentially do this in two different ways. You can say your strides are first going through all the experts, and then this is one sort of data parallel process, and then you start from zero after the each expert, or you can just replicate your the first expert in your data parallel process. Here, this choice allows you to sort of contain all your experts for a layer in the same data parallel process, and may seem like a better idea, but the communication overhead here actually comes through this all reduce operation where you're averaging across your gradients. So turns out having the copies for the same expert in the same process close to each other in devices gives you much less overhead in terms of communication that's needed. So the team used that architecture. So this was the architecture that was used for combining data parallelism and expert parallelism. Right, so that basically covers the system architecture choices and the optimizations done. Again, especially for the optimizations, there is much more detail in the blog post, so I refer you all to that one. For fine-tuning, we used roughly 1.5 million examples that consisted of 800 million tokens. The bulk of this was just general knowledge questions. A big portion, maybe a quarter, yes, was about coding. Half of the coding questions were on Python, and many of the others were on Java, JavaScript, and Go. Then there was math. These are essentially word problems with explanation traces about grade school math. And there was a very small number of identity questions as well. This is, in terms of actually teaching the model something, it's not that important, but for consistency of the behavior, identity questions are important. So to be able to teach the model that its name is Arctic, for example, and how it was created, etc. You sort of generate these sort of knowledge that the model has to be aware of, and then, of course, none of this is available in the public web, etc. So that's the sort of the usefulness of identity questions. And when you're training, fine-tuning MOE models compared to dense models, you run into a few issues that are not sort of very common in other architectures. One is expert stability is a problem. When you have a single sample in your fine-tuning, each token is again routed to a dedicated expert because there are 128. In a case where you have just a few hundred tokens in a sample, you might end up with a situation where each expert will see less than 1 tokens per example. This sparsity makes the training unstable. Few of your experts might not end up learning while the others are getting most of the tokens. And the pre-training actually kind of solves this in a similar manner, but through experimentation, the team also converged on a very similar setup for fine-tuning as well. What they did was, because having a longer sample is more useful here. Again, if you have a small sample, then you route that to your 100-something experts. Each expert will see less than one token. So if you have a very, very long sequence in your sample, then you can at least rest assured that through that thresholding process that I mentioned, each of your experts will get some of the tokens. So what the team did was they packed multiple examples into a single sequence. So instead of having a question and an answer, it was question 1, answer 1, question 2, answer 2 for each. Each sample was defined by concatenation of multiple questions. Another problem is training efficiency. So the way you handle fine-tuning is each sample is of differing lengths again, and you usually pad to your maximum number of tokens. In our case, this was 4,000. So given a short question and answer, in a single batch, the rest of the sort of values were padded with zeros, and this becomes fairly inefficient for a mixture of experts model. So the way the team handled this was, again, you instead of for a conversation looking at your first question and then your second question and sort of considering each of these as each of your turns as a single sample, we looked at the whole conversation as a single sample. This is a sort of simplification of the data set. Usually, when you have conversation, each turn in and of itself is a sample. But doing that was creating instabilities in inefficiencies in training. So the whole conversation was defined as the sample for fine tuning. Right. When it comes to serving, again, this is a very large language model. So we used a different sort of set of libraries to be able to efficiently serve this. The model is available in Hugging Face, and there is a model definition in Hugging Face as well. Our initial implementation used this inference engine called VLLM. And then again, for both training and inference, we used the DeepSpeed library. We actually contributed a few of these dequantization kernels that I mentioned to DeepSpeed as well. All the implementation here is by the beginning of this week has been upstreamed. I think Hugging Face is still in progress, but the VLLM and DeepSpeed has been fully upstreamed. So you basically need all of these 3 libraries to run Arctic on your own compute. But one challenge, of course, is because it's a large language, it's a fairly large model. It requires H100 node, a single H100 node. So it has a high sort of compute need. So one idea before the launch was we wanted to make sure to make the model available in as many places as possible. Snowflake has its own model garden called Snowflake Cortex. So if you have your data in Snowflake, you can run inference across your columns in batches, essentially, in Snowflake Cortex. So Arctic is available there. We also worked with quite a few partners during the launch to make the model available in their model gardens as well. Several of these are VLLM implementations. Again, we worked with NVIDIA to also add, they have a commonly used library called TRT-LLM. They have actually just added TRT-LLM support for Arctic and Arctic's architecture as well. So in the next release of TRT-LLM, NVIDIA will have support for it as well. But the model was available through a few APIs, through Replicate and Together and Microsoft and NVIDIA during launch, and a few others are coming soon. When I say it's available, just to sort of give a few examples, this is sort of how you call any model in NVIDIA's NIM API, I believe. And then here's an example of how you can call the replicate API and obtain results from Arctic. This is actually a code snippet from our own example reference app as well. So this generates the Arctic response through calling replicate, and replicate also provides a streaming endpoint as well. So you can sort of create a chatbot fairly easily, combining the replicate API with Streamlit. And I believe, yes, next slide actually gets into that. Other than making the model available from different model gardens, one consideration was we just wanted to make sure that on day 0, when we launch, it's possible to just chat with the model and get a sense of where it is good at as well. So the team built a Streamlit app that uses Arctic. Again, it used the replicate API. And here's a screenshot of that. You can kind of just adjust the different parameters for the model, and again, the skills that it is usually much better at are SQL coding and instruction following, but it is also very good at world knowledge as well, so you can use it as a sort of general purpose chatbot as well. And here's a sort of snippet from the Streamlit app itself. This is, I believe, a few hundreds of lines of code. And then the final consideration was it is fairly common to guard the output and input of a chatbot. And we have been partnering with Purple Llama from Meta to do this. And we use this in other systems in Snowflake as well, but we also used it in the Arctic chatbot that the team has built. The idea here is Purple Llama publishes this large language model called LlamaGuard. They have published one 7 billion parameter model, I think a year ago. Now, with the release of Llama 3, they released LlamaGuard 2, which is an 8 billion parameter model. What it does is it can look at the input to a large language model or the output generated by the large language model, and then it has this taxonomy of harmful categories, and then it classifies either the input or the output according to this taxonomy. That way you get a sense of whether there is a prompt-related attack, or whether your model has generated or was steered to generate a harmful response. Then you can either directly refuse if it's at the input, or if it's at the output, you can kind of just get ahead of the model when you detect that the output is harmful, and essentially reset the output. This app has a reference implementation for this method, and we also, again, use it for other products from Snowflake as well. Right, that actually finishes all the content that I wanted to go through. Just to recap, we talked about pre-training datasets, data prep. There's a dedicated blog about this. There are 2 blogs about the system level optimizations and the architecture. And I believe we are actually publishing the one on fine-tuning today. And then there's a bunch of model gardens, APIs that are available for serving the model. The articles are in this dedicated link here. We are calling the cookbook. Right now there are 4, and there will be, I think, up to 20 of these. We have drafts for several of these right now, and we will essentially be publishing them as we write them. And then finally, there is a dedicated GitHub repo in Snowflake Labs, I believe. The current work, the repo already has details about how you can run inference on your own compute. The current work right now is we are about to publish a recipe for running LoRa fine-tuning on Arctic. And we are also working on a dequantized checkpoint. So we have this dequantization kernels that we are using during inference, but one request from several sort of partners that we have been talking about was if we had a dequantized checkpoint that would actually allow us to load the model a bit faster. So we have generated that. We'll be publishing that as well. This requires a few changes on the way the VLLM setup works, so we upstreamed those changes as well. I think those landed actually last night. So there's sort of ongoing work here that are sort of to come in the next few days. Then there is some future work the team has been doing. The biggest focus here is on running inference using multiple nodes. So with larger MOE models, this is coming into more and more focus. Larger models will perform better. If you actually obtain large MOE models, you'll get better performing models that are running faster inference as well, but the size of the model is increasing quite a bit. This will require running inference across multiple nodes, and this is not a very common practice in the industry. So we are trying to figure this out and doing it efficiently, and we are also upstreaming all that work into VLLM as well. Another thing to call out is we are working with a few partners after the launch on fine-tuning Arctic and trying to sort of look into different versions of Arctic that are performing better at certain skill sets. If you have any sort of thoughts, ideas, collaborations in mind, please come find us. We'll be publishing blogs about this together with the partners that we are working with. Yeah, so we expect this to happen in the next few weeks or so. Another thing is we have an ongoing hackathon right now. I think this finishes next Monday, so Tuesday. Right. So we have a few more days left in the hackathon. This is using Arctic. You also get credits for running Arctic, and you can sort of use Snowflake and Streamlit to build interesting LLM apps using Arctic. So if you want to check out the details, please check out the hackathon as well. And finally, we have our annual summit coming up at the beginning of June. And during the summit, there is going to be a dedicated Dev Day in June 6th. So we'll have a booth there. Several members of the team will be there as well. I'll be there as well. So if you want to meet other builders and have fun, please, if you're sort of near San Francisco area, please feel free to check that out as well. Oh, yes, it is free. that is an important thing to mention, yes. And I think that was actually the final slide. Yes. Thank you. I think we are doing well on time, so I can take questions if you have them. Yes, please.
First things first, I really like this. Secondly, can we have a presentation for ourselves? When can we get it? Where can we get it? And three, how would you exactly determine the quality of the data you're actually using? I know you're checking out through a lot of different sources, but again, how do you determine what's better than something else? How do you refine this to get to your certain point, so get something that's more specific?
So for when it comes to like general purpose data, web data, again, you rely on you have to basically have a reference high quality data set. For us, this was refined web, and then you also have to have a large pool of web data that's available. So, and then you have to figure out how to filter out, how to sort of obtain smaller subsets of that large pool that is as high quality as the reference data set. And you do this through many ablations. So you train smaller large language models over and over again using different configurations and obtaining different subsets. Some of it is more art than science as well. How you run the ablations matter, what you use for comparing across the ablations matter as well. But I would actually defer you to the blog post about how the data set was obtained. I think this talk it will be available to, I don't know if slides are usually available.
We'll post the slides in the forum link, so if you go back one slide. This actually links to a forum thread.
Okay. So if you go to the forum link, there will be slides there. And again, within the slides, I also link to the cookbook blog articles as well. Actually, you can just search for Snowflake Arctic Cookbook, and it's the first thing that comes up as well. And there will be many articles that we'll be publishing. Yes.
Apologize if I missed it, but is Arctic a general LLM or is it specific to particular content?
So it does fairly well in general purpose usage. So when it comes to word knowledge, math skills, it is actually at the top tier compared to other open source systems. It is much better in what we are calling enterprise skills. So these are SQL generation, coding, and instruction following. It is performing at state of art or close to state of art. Yes?
How many people are on the team?
This was a team of roughly 20 people. Of course, there are many aspects of actually training. So there was a dedicated team for obtaining data set and systems level optimization, the team that's actually working on the cluster and infra, etc. But 20 or so. Yes.
I'm curious about the pre-training process. I think you said it would take a while, maybe X number of weeks. I'm curious how you know, like, if it's going to take a year to train, that's obviously too long. How do you kind of keep track of and like know when it's going to finish?
Yeah, so for Arctic, it was essentially 3,000 GPU weeks. So depending on the size of your cluster, the way you do this is you run, again, ablations with the architecture implementation in mind, and then you obtain essentially a communication bandwidth value. And then given the size of your cluster and given the data set size that you want to go through, if you want to go through 4 trillion tokens, for example, and if you have, I don't know, 2,000 GPUs and your computation is running at a certain certain rate, then you can basically do back of the envelope calculations to obtain the number of weeks as well. Again, it obviously scales with the number of GPUs you have, so the more compute you have, it will take less. But there is also a lot of value in obtaining an efficient system so that you can kind of go through a large amount of data efficiently. For Arctic, it was 3,000 GPU weeks. Again, not disclosing the number of GPUs used, but relatively that 3,000 GPU weeks to obtain a performance like this is fairly efficient. Yes.
Regarding the number of experts that you use, what is your intuition? Do you think that you increase this number to get better results?
It really depends. It depends on your the total number of tokens, your essentially training horizon. For us, we through ablations that we run for this version of Arctic, 128 was turned out to be the right number. But again, that sort of brought in its own challenges, and the team had to sort of write specific kernels for that, to optimize the system. You can also get efficient, depending on how much data you have in your system. You can get an efficient setup with a fewer number of experts as well. Though, again, it's a the trick here was to actually co-design the system and the architecture at the same time. So usually what happens is you have a certain amount of data budget, you have a compute budget, then given that you start from there and you run a bunch of simulations and you kind of figure out the best architecture. But again, the MOE is fairly new, so there are not a lot of easy degrees of freedom for training MOE models. And one goal for us to actually figure this out, like can you actually create large MOE models and run them efficiently? And some of the work that we have done and will be publishing is around that.
This question from the audience: how many of you are Snowflake users today?
Any other? Yes.
Kind of a weird one. Excuse me. So in the training of the mixture of experts, do you assign experts specific things, or is that like an entirely self-organizing process? And do you think a model can be made very interactively, even though it might be
Yeah. So the experts here is essentially, it's actually somewhat of a confusing name, because those expert modules are replicated at each layer. So there is no expert for a specific topic that comes out of that process, essentially. So each token goes to a certain expert in a single layer, then it can go to another one and another one and so on. And there are many, many layers here. So the experts at the higher order layers, they might be mapping to certain, like more like higher level abstraction concepts when it comes to token, but it really doesn't really. It is hard to say that it maps to being better in a certain topic, for example, and they are not actual domain experts. Yeah. Yeah. Mm-hmm. Yes.
Sort of ask a clarifying question for him. When you're talking about the difference between sort of dense node versus an expert node, what they are is really it's the same construct within the neural net. The only way, like the way that they're distinguished between the two is how they're treated during training.
Yes.
Is that correct?
Yes. Essentially, the same architecture is kind of duplicated across, and then during training, depending on the tokens that they get, they change differently, and then they turn into a more sort of they get an affinity towards a certain type of token. And again, it's hard to map this to a domain or anything like that, especially for the lower layers. Yeah. Any other questions? Right. Thank you again.